electrons, and capital K is the average of the momenta between initial and final electrons. So there will be a term proportional to P mu, and there will be a term here proportional to P mu times gamma dot K. So K with a hat here is gamma dot K, stands for that. So you can write this in different forms, but you will always have three independent structures. Now, the reason why it's written in this specific form is because if you make now the approximation that you will have only one photon exchange, then one of these will be exactly 0, and these two, which are functions of the variable, a crossing variable mu, which is the Mandelstam variables S minus u, and T, which is the momentum transfer here. I denoted this by Q squared before. It's the difference between electron momenta squared. So they are functions in general of variables mu and T. And in the one photon exchange approximation, they become form factors, the Dirac form factor and the Pauli form factor here, or magnetic form factor actually, and Pauli form factor. And this function vanishes in the one photon limit. But if we want to go beyond one photon, we have to do the general analysis, and then, as we have argued, you need three independent amplitudes. So you will, the interference between 1 and 2 photons will give rise to corrections to these first two terms, and will give rise to a non-zero value for the third function here. So, okay, let's have a look. So I just explained you that two of these structure amplitudes in the one photon limit, they're just given by form factors which only depend on Q squared and not on the energy. And then they get corrections which are labeled by deltas here due to two photon effects. And the third structure amplitude starts at 0 and just starts at 2 photon correction. So one can, just for the sake to have easier formulas, one can make three independent observables and basically take the ratio of this 2 photon part relative to this 1 photon part of the form factors, and taking the real part of this, because we will need the real parts of these amplitudes. They are in general complex. And one denotes this by these capital Y's, 2 gamma with index magnetic. Then there is one combination for the electric one, which one can define in the same way as we have done it for the form factors. And then there is the combination for this third amplitude, F3, which is multiplied because it always comes with a certain kinematical factor. So this is taken out and divided by the magnetic form factor. So there are three basically structure amplitudes proportional to this 2 photon pieces, delta Gn, delta F2, and delta F3. And now one can look at the same observables which I've shown you before, which is the cross-section, which is the ratio of these polarization components, transverse to longitudinal, and then, let's say, one of these components, the longitudinal, relative to the value in 1 photon exchange. And so before explaining you these formulas, so let's first look at what is shown only in blue, and this blue is the result if you have just 1 photon exchange. So we have seen, if you take the cross-section, it was Gm squared plus epsilon over tau Ge squared. So if I divide this here, so this is the so-called Rosenbluth formula, which we have seen before. We have seen that this particular combination of polarization observables was proportional to the ratio of electric over magnetic form factor. And so I've not shown that to you, but if you calculate the longitudinal polarization components separately, and so you divide this value, you get by definition 1. So the 1 just means, so you have here the 1 photon result for the longitudinal component. Now, if you calculate the interference with 2 photon, it's an exercise which is, okay, a few pages, but not that long actually. You will find corrections where these 3 structure amplitudes will enter, and they are shown in red. And they have prefactors, and depending on which observable you are looking at, so these prefactors are different. So, so here you see that, for instance, the magnetic one comes with a 2, and here it comes with a factor G over Gn, and here you see that it comes with G squared over Gm squared, for instance. So in principle, if we have 3 accurate measurements of 3 observables, there are 3 independent observables, one can deconvolute this and extract these 3 amplitudes. So now this has actually been done, but only for one specific point in Q squared up to now. These are tough experiments, so this was done actually for the unpolarized experiment about 10 years ago. So this is the traditional Rosenbluth plot where one has an epsilon dependence here, and so if one would have only one photon exchange, one will get a line which is actually drawn here by the blue curve. And the data show basically also a linear dependence, but with a different slope. So a different slope means that the ratio of G over Gm will be different extracted from here compared to the result from one photon. And then more recently, actually only a few years ago, here also these polarization data for the ratio of transverse over longitudinal and for longitudinal relative to its one photon value have been extracted for different epsilon values. And for this ratio, it's basically independent of this epsilon, which means, so if it's a constant, this is just the result for one photon exchange. If we look now at denominator separately, or numerator equivalently, one sees a deviation from 1. So any deviation is proportional to these 2 photon effects, which is in the range 2.5 to 3%. So now, okay, let's then extract. So basically one can now come back to these formulas here. Sorry. Come back to those formulas. So we have data points for 3 experiments at a fixed value of Q squared. And one can, at this value of Q squared, one can extract these 3 amplitudes, which is these two photon amplitudes. And there are 2 bands here, because one needs, of course, data over the whole range of epsilon, and there's a range at lower epsilon where there are not enough data, so one has done a theoretical parameterization here. In the range where there are data, the 2 bands coincide, but in the range where there are no data, so there are ambiguities here, the solution, that's just uncertainty for once. And that's the systematic uncertainty. So this is shown here, the systematic uncertainty of the data. So the main result here is, first of all, the size. So one gets an effect which is typically like 2%, and one has a linear dependence. So this means that these 2 photon amplitudes are not constant, but they depend on this photon polarization parameter, or the energy variable. And it's this linear dependence which is responsible for the 2 different extractions of the electric over magnetic form factor, because this linear dependence changes the slope in these Rosenbluth plots. And so basically, 2 photon amplitudes which are in the range of 2 to 3% are sufficient to explain this big difference in the extracted form factors. Okay, now, of course, one would like to see these results at different values of Q squared. They're unfortunately not available. So if we want to calculate these 2 photon corrections to the lamp shift measurements, or to electron scattering measurements at low Q squared, we need to extrapolate to low Q squared. But there are some things which one can say model independently. If we go to very small Q squared, so typically 10 minus 3 GV squared, so where experiments are being done to extract the radius, this 2 photon correction factor to the cross-section can be split in a part which is well calculated, which is here called delta 2 gamma infrared. This is just due to soft photons. So if you do a field theory calculation, you can always split off that part. And then you will get an expansion in Q squared. And the leading term is the leading terms are non-analytical. So the leading term has been calculated quite a long time ago, actually, by Feshbach and McKinley, 48. And this is just due to Coulomb photons. So if one does a calculation between a spin-1/2 particle in a potential, for instance in Dirac theory, you take a potential, you calculate this, you will only calculate here with the gamma 0 term, so it's basically the 0 component of the full current operator. So it's just saying that you consider static potential. This gives rise to a correction term which is proportional to the square root of 1 minus epsilon, and this epsilon vanishes at very low q squared, goes to 1 at very low q squared, so the numerator here is proportional to square root of q squared.
So does it correct the 1R equivalent potential? Does this contribution?
Yes. This gives you a correction to that, and in momentum space it goes with square root q squared. So that's this Feshbach correction. So which is usually applied when you have charged particles. So it's multiple scattering. So now you can go beyond this, and the next term are logarithmic terms, and the next term comes also from this diagram, but not making the assumption anymore that you have here just a gamma 0, just keep the gamma mu term here, and then you get q squared log q squared terms, log square q squared terms, or q squared log q squared terms, the 1. And then you get a term which is denoted here by A, and this A is the first term where inelastic intermediate states, so if you have here like excitations of the nucleon, will enter. So actually this result has been obtained also some time ago, but has been overlooked in the literature. Recently has been evaluated numerically. So this is at the level where you have logarithmic corrections with single logs, you will get effects due to intermediate states. And then you will get analytic terms which are still smaller at lower q squared. Now, just to give you an idea how large are these effects, so this is shown here for kinematics which correspond with the experiment which has been done in Mainz, so to extract the proton radius, which was 180 MeV. And this is shown here as function of q squared, so typically this is small values like 10 to the minus 2 GeV squared. So this is this correction, delta 2 gamma, so this is 1% typically. So one sees the green curve is the leading effect due to these Coulomb photons, and one can explain basically a large part of this effect. And so the effect which is coming from these log terms, so the leading analytic corrections here, and non-analytic corrections are given by this red curve, and then the blue curve is taking this full box into account with intermediate state. And so what is shown here is just the same presentation as on the left, but relative to this green curve, the Feshbach curve. So what it means that the effect of all these terms here, which go beyond the Coulomb corrections, is something like 3% on top of this. So the 3% on top of this, depending which corrections you are taking, 3 or to 4%. So it means that we understand these two photon corrections because this 1% actually is very well understood. The green curve, there is no doubt about it. So the only doubt is here, how large is this? And this is basically an effect of something like 3 to 4% on a quantity which is 1%. So that's why we are pretty confident that one understands these two photon corrections at very low q squared, at least to extract the electrical radius. If one goes at larger q squared, these effects of course start to grow, and the deviation here becomes larger. So I'll come to this. Okay, so if you want to go beyond such a very low q squared expansion, which one can just write down analytically, so we have to do the same as what I've shown you in the case of the muonic atoms last time to calculate hadronic correction. One has to calculate such a box graph. Now, we are in a less fortunate situation here, because in the muonic atom we were saying the muon, or the electron, is basically at rest. Okay, relatively speaking, it's at rest. So which means that the momentum which is transferred between the electron and the proton in an atom is proportional to the reduced mass times alpha. So it's a very small number. So you can approximate this in first approximation to 0. And then we have seen if this momentum is equal to that, then we had this loop here where the momentum which flows there and which comes up here is the same. And that's which allowed us to apply a forward dispersion relation. Here it means we can relate this to forward Compton scattering. Forward means the same momentum comes in and out, and this is why one can relate it to structure functions. If you have now a finite momentum transfer, because if you do scattering, you scatter at some finite angle, so this momentum is not equal to that momentum, so the momentum transfer T is minus what is called capital Q squared in electron scattering, then the two momenta in the loop are not equal anymore, so you cannot relate it to a forward structure function. Of course, you can still apply optical theorem, but now you will have here to sum over all intermediate states. So you have nucleon and then pion nucleon and so on. So it becomes more complicated, and because each of these processes here on the left and the right is a different amplitude, so you have a non-diagonal overlap of these amplitudes. Now, if we have seen there are three independent amplitudes, so this magnetic, F2 and F3, we labeled them, which are functions of energy and momentum transfer. So if we use these three functions at a fixed value of momentum transfer, we can look at its behavior if we change the sign of the energy variable. So this is called crossing symmetry in quantum field theory. And so when you change the sign, you can have either even or odd functions. It turns out two of them are odd functions and one is even function of this energy variable. And now the two odd functions, one can just write linear combinations of them. So the reason why one is doing this is because the high energy behavior, if one wants to go to nu going to infinity, is improved for these two amplitudes relative to the original ones. But it's only a technical argument, so there's nothing fundamental there. And now, if one has amplitudes which have a good behavior on the crossing, one can write down dispersion relations which relate the real part of such a box diagram to the imaginary part. And so there are two types of dispersion relations because it will depend if the amplitude is odd in U or is even in U. So you see the power which is standing here is different from here. So here, this is the integration variable. So one integrates basically over energy, which is labeled here as mu prime, from 0 to infinity, and then one has to close this contour. Now, if at high energy this drops sufficiently fast, so faster than 1 over the energy, one can drop this contour, and the only contribution which one gets is from the cuts in such a diagram. So the leading cut is the nucleon cut, the next to leading cut will be a pion nucleon cut, and then you have two pion nucleon cut, and so on. So each of these cut contributions will give rise to an imaginary part. So one can measure these imaginary parts from experiment, and then you form the interim and you reconstruct the real part. So that's how, in principle, you calculate these quantities. Now, in practice, so this has been implemented partially, because it's more complicated here. So I will show you here, just for the sake of this lecture, a simple application where one can compare directly with a loop diagram calculation. Namely, if you do a box diagram calculation, but you do it not in field, not with point-like couplings, but with couplings which involve form factors. So in general, such a calculation is not guaranteed to give you the right result, because it would qualify as a model calculation. Now, and that's basically what had been done before for such box diagram calculations. So if you have here, for instance, the anomalous magnetic moment, or the Pauli form factor, which has a momentum dependence. So in general, so this is not a renormalizable vertex, so if you calculate such a diagram, even if it's finite, it's not guaranteed that it gives you the right result. So only if you have renormalizable vertices, it will give you the same result. However, if you do dispersion relations, you will cut this diagram, so you put the intermediate state on shell, so you will only need the on-shell information. So this will guarantee you that you have there the right behavior in these vertices, and then you reconstruct the real part from the above dispersion relations which I've shown. And if one does this, so just as an example here, the momentum transfer like 0.1 GeV squared, and this is shown for one of these three amplitudes. This is this amplitude F3, which is 0 in the one photon approximation, as function of this parameter epsilon from 0 basically to 1. If you calculate this directly as a box diagram, using here anomalous magnetic moments in this example, so you get a specific curve, which is shown here. If you calculate it using dispersion relations, you get a different curve. So the shape is the same, but the magnitude not. So, and if you do one subtraction, then this is shown on the right here. This is shown for two different subtraction points. Let's just look here on the lower curves. There are actually two curves, one on top of the other. If you do a subtraction of this diagram at one specific point in energy, you will get such a curve. If you do the same with the dispersion relation, you will fall exactly on the same curve. So what does it mean? It means there's only one correct calculation, and the one correct calculation is the dispersion calculation, is this one. If you prefer to do a box diagram calculation, you should do one subtraction to be in agreement with this dispersion calculation, and then the subtraction constant you should fit from experiment. So this is just a proof of principle here that you get the correct off-shell behavior of these two photons. Now, this has been applied to data actually. I will just be very brief here, just to give you a flavor of the kind of comparison. So this is shown, this is again this two photon correction at low Q squared, like 5 10 to the minus 2 GeV squared, and here at 1 GeV squared. And the blue bands are the experimental numbers. So the experimental extraction, this is the same experiment which is giving rise to the proton radius extraction from electron scattering. So the most precise electron scattering experiment. And there are a number of curves which are shown here. So there are curves where one shows this box diagram calculation, which is not necessarily correct because it doesn't have the correct off-shell behavior. And then one has subtracted dispersion relation calculations, and there are three of them which are shown here because they depend on where you do the subtraction. So they're, by definition, if you do, for instance, here the green curve is subtracted at the point 0.8, so by definition you go to the blue band at 0.8, this goes at 0.5, and this goes here at 0.3. So you can do subtractions at different points and then do this comparison with data. Now, of course, you will say, yeah, there is some arbitrariness, but the arbitrariness is actually not in the theory at this point. So, okay, of course, it depends on the dispersive input here. The arbitrariness is on the data, because the data have assumed a specific form for these two photon corrections, and that's what you also were asking. If you go to larger Q squared, this becomes even more pronounced, this band. And the theory shows that if you go to smaller values of epsilon, and that's basically going to backward scattering, these two photon effects become much larger, typically like 3%. So we have seen here at very forward angles, these effects are typically like below 1% and are relatively well understood in terms of this Coulomb scattering. But if you go to backward scattering, which you need to extract the magnetic radius, you will get much larger effects. And so basically what has to be done now from the experimental side is with this new framework to extract these two photon corrections, and then these blue bands will basically also here go up. This will be just constrained. And then one can do a more accurate extraction of this radia. Okay, this is just a comparison with polarization effects here. So at low Q squared, basically, these polarization effects are consistent with a constant. So again, the blue band is the analysis of these two photon effects from unpolarized data. They are consistent with the data points, so it just means that in polarization observers, these effects are very small. Okay, just to show you what is being planned here in the next couple of years. So there are measurements both at Jefferson Lab, at Novosibirsk, and Olympus at DAISY, where one would like to, one plans to access as function here of q squared and epsilon, so this is the range where one will have these new data, where one likes to access the difference between electron and positron scattering on a proton. Now if you have electron scattering and positron scattering within one photon exchange, it's just proportional to the charge squared. So if you take the difference or the ratio, it's just 1 in the ratio. Now if you have the interference between 1 and 2 photon exchange, you will have a sign change between them. So from the deviation from 1, you have a direct measure of these two photon effects. And just to show you, this is basically the initial, the state of the old data. So the old data from, so at SLAC, people have already tried this, but within the precision, which one had in the 1970s or late 60s, there was no chance to see it. But the new data here at Novosibirsk clearly show an effect of a few percent. So these are these red points. And this was at a relatively low value of q squared, so the effect is supposed to increase with larger q squared. So the largest q squared experiment, which has been done actually already, was the last experiment at the DAISY ring. So Doris is one of the rings at DAISY, which has done such an experiment with 2 GeV electrons and q squared in the range up to about 2.2 GeV squared. And so what you see here is just the large arcs are the old data, and this is the projection of the new data. So they're just shown arbitrarily here because the analysis is not complete. And there are different curves being shown actually. So one of these, the blue curve, I would like to emphasize, or the violet, sorry. So this one is the 2 photon effects, which were the blue bands, which I've shown you in the previous plot. So typically you expect here to see effects which can go up to about 5 to 6% in this ratio of positons to electrons. So this will be very important to really pin down this in a quantitative way. Okay, so let me spend the last 2 minutes or so. Is that still fine, or should I? Sorry, I'm just looking here to muon scattering. So we have seen that if we want to understand the electron and muon system, we have to do independent measurements on electrons and muons. And so coming back now to what we were arguing here. So we were saying if we have electron scattering, we only need to look at the helicity conserving amplitudes. There were 3. But in the case of muon, when you do muons has much larger mass, so 105 MeV, and if you do scattering of a few hundred MeV over C muon beams, you cannot neglect this mass anymore. So muon is not ultra-relativistic. And then you have to do the full analysis. Instead of having the 3 amplitudes, you need to take into account the 6 amplitudes. Now, you can also do that. So if you take the mass terms which are different than from 0, so you see all these terms are proportional to a lepton mass. And those of you who know these helicity arguments in field theory, you will see you have L bar L, so this lepton propagator. This is a scalar term. You know a scalar will flip helicity. And here you will have L bar gamma 5L, pseudoscalar flips helicity. And before we only had L bar gamma mu L, a vector conserves helicity. So you have terms which are all flipping the lepton helicity, and then you have again some choice how to parameterize it. So this was done here in one way, and this gives you these 3 more amplitudes. And you can do the same analysis also for the 2 photon correction. Now, instead of having only the structures before, there's an extra term here, and so one can calculate this, and this has been done. And just to show you the kind of effects one has, so there is quite some difference actually. So if the muons were just electrons, so you would get 2 photon effects here in the kinematics. This is beam momenta of muons, 115 and 150 and 210 MeV over C. It's exactly the momenta which this new experiment will measure in 3 years from now. So if the muons were electrons, you will have this curve as function of q squared, which is like 10 to the minus 2, here GeV